Ciao! Welcome to this session. My name is Alberto Marri and I am software engineer at Embit, which is an Italian company acting as a player in the LoRaWAN world by many years. Today I will explain you how to develop your secure LoRaWAN solution, adopting Embit hardware and software development kit, and exploiting the joint effort of Microchip and dating industries. Let's start with the presentation. Micro-embedded approach on LR1276S provisioned dating industries LoRaWAN solution. Who is Embit? Embit is a company which produces and designs wireless modules with a sharp philosophy. Embit Module is not only a transceiver. Indeed, Embit wireless your idea. Customers come to us with their idea of IoT solution, and we design and provide them. Our module, each Embit module has an MCU integrated. In this way, you can use the micro-embedded approach. You can develop your solution and your own application directly on the wireless modules. So the module has MCU plus the transceiver. You don't need any other external MCU. You can reduce the cost and space of your solution. And in order to allow you to develop better and faster your solution, Embit provides a software development kit. Today, as I told you, we will exploit the TTI and Microchip secure solution. They developed together this secure solution that enables secure key provisioning and secure cryptographic operation through the hardware crypto element developed by Microchip ATECC608A. The root keys are directly injected in the chip. It is not possible to extract them, and during the join procedure, the session keys are derived starting from these root keys in both two sides, the join server and the module sides. In this way, a pair of identical key is created without any kind of physical exchange between the network server and the module. In this way, the weakness of the LoRaWAN communication is drastically reduced. Then, on top of this solution, we will exploit the Things Enterprise Stack, which is offered as hosted software as a service. The Things Enterprise Stack offers a solution to build open and private LoRaWAN IoT networks, where you have the control on the security, on the life cycle of the nodes, on their status, and on the total cost of ownership. It is proposed as a multi-tenant environment. In this way, each user has its own isolated network, and only the underlying layers are shared. In this solution, each cloud-hosted cluster contains a joint server for convenience. And as I told you, the joint server stores the root keys, derives the session keys, and sends them to the network server and the application server. It's this the solution that adds security to your communication to the LoRaWAN network. About Embit, today we will adopt the module LR1276S, which is one of the smallest LoRa modules available on the market. As MCU, being an Embit module, it has an MCU, and it is the Microchip SAM-R34, and it is full LoRaWAN Class A and Class C compliant. Obviously, it has several interfaces, and today, for example, we will adopt I2C bus in order to extract data from the sensors. Obviously, being LoRaWAN, being taught for LP1 network, it is an extreme low power module. And we will adopt them with the crypto unit ATECC608A with pre-provisioned key by dating industries. This secure element can contain in this way a secure identity, and obviously it contains the root keys compatible with LoRaWAN 1.0x and 1.1. Purchasing this module, you have 1 year of dating industries joint server access included, and the module is network and application server agnostic. In this way, you have the possibility to provide a unique, trusted, protected, and managed identity. This solution is a ready-to-use solution. In this way, you can speed up your process, and sending the join request to the LoRaWAN network server, you will exploit all the functionalities I described before to verify the identity, and in this way, fraudulent devices are not able to join the network. This is the schematics. Microchip generates the JSON manifest file and send it to Embit. In this way, with the module, you can upload the JSON file to the TTI joint server and claim the identities and the ownership of the module, and then starts the secure, trusted, managed authentication and join procedure. In this way, you are able to create your LoRaWAN solution and on the end device side in few simple steps. This speed up your process. The crypto element obviously is pre-provisioned with these root keys, and these root keys remain isolated from the system, so the sensitive keys are never exposed to the supply chain. This way, you create your solution in few simple steps. This is the pinout, and this is what we will use today, the Embit LoRaWAN evaluation kit. Obviously, it has the module, it has an SMA connector to connect the antenna. There are two sensors, the temperature and light sensors. There are two kinds of programming connector, two buttons, one for the reset, an LDO, and a micro USB to send command and to power it on. Hands-on training. What we will use today? We will use indeed the Embit LoRaWAN evaluation kit, which is this one, and we will use the module pre-provisioned with TTI keys, root keys. The software we will adopt is the IDE Integrated Development Environment Atmos Studio 7, which is a free one, and we will adopt Embit libraries and software development kit. The code is written in C. The goal of this presentation is to set up your LoRaWAN secure node using the joint authentication process on dating industries joint server, and program the module using the micro-embedded approach to send data extracted from the sensors. So let's start. The first step is to claim the identity and the ownership of your device. Following the guide of the Things Enterprise Stack, there are 5 prerequisites, which are having a crypto unit secure element, and we have it, the manifest file, and we have it too, access to the Things Industries cloud hosted, having an application in the Things Industries cloud hosted, and know the Things Industries joint server address. This is our instance of the joint server address, and now, having all the other prerequisites, we go to create our application. We had an application, clicking here, the owner it's me. My new application is test for TTI virtual conference. Application I cannot put uppercase. letter, application name my test application for virtual conference, and I can skip the description, and then I click here on create application. In this way, the application is created. Now, to claim the ownership of the device, I have to click here to import my device, import devices. Import device, file import, and I have to select the format of my file, which is a Microchip ATECC LoRa manifest file. Format information JSON manifest file received through Microchip purchasing and client services, exactly. And I have to select a file from my file. Then I can create my devices clicking here. For the sake of time, we have yet created and claiming the ownership of our devices on app 1. And here you can see the list of all our devices. It's quite interesting to know that every time we created an application on the joint server, it is created also in the cloud-hosted test-TTI virtual conference. Having done this operation, we have only created our devices, and then now we have to register and activate it. It is possible to do so following the guide in the Things Enterprise stack to register the device, and then to activate them. To do so, you need to use the command line interface only, CLI. At this point, we can now look at the code. This is the IDE Atmos Studio 7, and this is the code written in C, as I told you. Obviously, our project started by the main.c, and the first function that I would like to show you is print ACC info. This function prints the public keys written inside and injected inside the hardware crypto element using the function readByteZone, and then it prints it in the serial page. The communication between the SUMR34 and the crypto element is based on an I2C bus. Then we can start with the main. Obviously, as every embedded system, it starts with system initialization, where clocks are configured, board is initialized, and also the hardware events are initialized. Then we have the initialization of the delay driver. This is the configuration of the I2C driver, and in this case it is quite important because we will read the data from the sensor using this I2C driver. And obviously the sensors are initialized too. So both sensors, the temperature one with its initialization function of the driver, and the luminosity sensors with the configuration function. After this simple step, the stack is initialized, and the first function to be called is mode demo init. As you can see, when CryptoDev is enabled, print ACC info, the function I showed you before, is called. Mode demo init is the first function, and obviously it is initialized the LoRaWAN stack. To the LoRaWAN stack are associated two functions: demo join data callback and demo application data callback. Join data callback is a callback that acts just after the initialization, the join procedure, and it deals with that. And application data callback go to start this process in the application layer. When the initialization is successful, it starts the join procedure. The join procedure implemented in this code is an OTA procedure, over the air procedure, and the application AOE and the application key are sent to the network server, and a device address is assigned. Obviously, we have to set this kind of parameter, and these parameters are set in the function mode set parameters. It's quite important to look at this kind of the code. Indeed, if crypto device is enabled, the Boolean variable crypto dev enable is set to true, and in the LoRaWAN stack, this attribute is set to true. So in this way, the module knows that it has to derive the session keys starting from the root keys read and written in the crypto hardware element by Microchip. Then, when the join parameters are set, the join request is sent in using the function LoRaWAN join. If it proceeds all in the right direction, send data function is called. Send data function is a function that fetch the data from the sensors and send it to the network. So the first function to be called are get light reading and read temperature. Obviously, our function taken by the driver of the sensor, so the light is red, reading a certain register of the sensors, and the same is done in read temperature function. So also in this case, a register of the sensor is read in order to fetch the data about the temperature. Then the packet is prepared, and it is prepared according to the Cayenne rules. Cayenne is a way to write a LoRaWAN packet, and writing the packet and sending them in this way, your data becomes human readable since the network server. So looking at the packet you sent in the network server page, you are able to look at your data in a human readable way. When the packet is prepared and is ready, we can send it using the function LoRaWAN send. And at this point, we send the packet and we finish, in theory, our application. So now we have to build the code and to program our module. The first step to program it is to set up the device programming under Tools page. The tool is SAM ICE. The device it is SAM R34J18B. The interface is WD. We press apply. We read the device signature and the target voltage, which should be 3.3. Now we are able to compose, build, and inject the code inside the module, pressing this green arrow. The code has been built and now it is programmed. To read the serial interface, we adopt PuTTY, but first we look at the number of the COM of our module. It is COM 18. Now we are able to open PuTTY. We set up the font, a bigger one, okay, and we log in COM 18, and the speed is 115200. We reset the module, And first, we can look at the function that I showed you before, the one print ACC info, the one which prints the device ID, the application ID. Our device ID ends with 79B. Now we select the application, the demo application. We select the bandwidth, and the GEN request has been sent for this bandwidth. We wait for the answer. Yes. Joining successful, and this is the device address assigned. Now we are able to send data, the luminosity, the temperature. The data has been sent, and the transmission is successful. To look at the data, if it is coherent or not, I switch on the lamp of my smartphone and I put on top of the sensors, and I send again the data, and the luminosity value should increase. This one, luminosity 2315. The data has been sent, and the transmission is successful also in this case. Now, to look at our data, we can go to the web page. To look at our data, we go to the cloud hosted page on applications, application 1. We look for our module, which is the one which finished with 79B. We open this page and we look at its activity. We take again putty, we send another packet, and we look at the packet that has been sent. We are able to look at the packet, and as I told you, using Cayenne rules, we are able to have the data in a human readable way since the network server. So luminosity 310 and temperature 21, as written in the serial terminal. We can look at the packet also on the gateway side. So always in the cloud hosted page, we go to the gateways. The gateway connected is this one, gateway 1. We look at the activity of the gateway. We send again through putty another packet. The packet has been received. It's quite interesting to know that in this page we cannot look at data. It's obvious that who owns the gateway does not need to access, and it is not allowed to access to all the data. We can look only at the metadata of the packet, the timestamp, the RSSI, the SNR, and so on. This ends my session, and now I'll show you my contacts. My email address alberto.marri@embit.eu, the email address to ask some general info@embit.eu, and our web page www.embit.eu. We are ready to receive your question, and it will be a pleasure to try to solve your doubts. It has been fantastic to be part of this event. I hope you enjoy this session. So now, stay safe, stay at home, and ciao ciao!